Hello there, and welcome everyone to our webinar today in a Halloween theme, Kubernetes Nightmares, the dangers of poor resource management. Seemed appropriate. Andrew's content is tight and focused on bad things that can happen if you don't manage resources well in Kubernetes. Very powerful, flexible platform that is, as I noticed in the last couple of weeks, I think the largest or most prolific open source project since Linux. So Kubernetes is here to stay. We have many customers that are going large scale with it, but it's complicated. And so we're going to talk about some of the things that can happen if you don't manage resources appropriately. So over to you, Andrew.
Okay, thank you, Chuck, and thanks everyone for joining. Let's dive in. A quick note on who we are, if you don't already know. We're AI-driven analytics that for cloud and container. And I'm not going to talk a lot about cloud today. I'm going to talk a bit, but I'm going to talk in Kubernetes, obviously, to really strike that balance of making sure everything works properly and minimizing cost. And we find out there, obviously, cost is a huge driver across cloud and containers, and that's usually a big business driver, but you can't go after cost in a way that harms performance. And so we have a very big focus on that. And I'll talk a bit about that. Usually in Kubernetes environments, we find a lot of stuff that's just purely performance oriented or reliability oriented that we can fix as well. So we cover the major cloud providers and of course, Kubernetes, the providers on their own, plus Kubernetes running on these providers, plus Kubernetes on-prem and OpenShift and all the different variants of Kubernetes. But the last thing I'll say here is that it's very important that we do both of these because to properly optimize the Kubernetes environment, you need to also look at the cloud nodes and skill groups that it's running on, because that's where you make the changes to save the money. And so being able to go very deep up and down that stack is very important. If we talk about resource management, and if you look at that kind of classic struggle of making sure you have enough capacity and not too much, and we saw the emergence of FinOps in the cloud to make sure that you're not spending too much. But usually it's the app teams that are making sure that they have enough. They're responsible for the apps working. They usually care about cost, but usually more if they've gone over budget. I was talking to one of our customers last week where they're saying, yeah, it depends on what month. If you're over your budget, then cost is the biggest problem. If you're not over your budget, then risk is the biggest problem. So there's kind of competing requirements here. And then in between them, and this is where it's a bit different than just pure cloud, where I can go and say, just make the instances smaller and you'll be fine. You can't change one thing in a container environment without changing other things, without affecting other things. And of course, these platform owners in between here that are kind of also in the mix. So they have responsibility for certain aspects of the operation. The SREs have certain responsibility in here as far as what they're deploying and what they need to do. And then the FinOps has a different responsibility. And it all becomes very complicated. So the money spend is actually incurred down here. So whatever actual infrastructure you're running on, I'll talk about Amazon scale groups and scale sets and things like that. It could be bare metal. That's what costs the money. But that's being driven indirectly by what is being input here as the requirements. And I'll talk about this in a minute. If those aren't correct, it affects the entire equation. But like I said, you can't just go and modify things in isolation because all of this is intertwined. So everything is affecting everything else. If a container is too big, well, it actually might be holding a bit of capacity on a node for one that's too small, and they might actually be helping each other. So you can't just go and downsize things if the nodes are already having resource pressure. So again, it's highly interrelated. It's more complicated than cloud, and it includes cloud optimization because that bottom part is often optimizing the cloud instances, but that can't be done without optimizing or looking at the containers as well. And to that end, that's exactly what we do. And I'll talk about these things a bit. So I'll describe a bit about the analysis of the containers themselves. We have an interesting visualization that lets you see how wrong your containers are. I'll talk about that. And that lets you know the inputs into the equation, if they're right or wrong. And then we also analyze the actual running infrastructure and how is it scaling and what's its replication pattern and should it be on a different node type or different scaling parameters. And they're highly intertwined. They feed each other. And as you optimize the top, the bottom answers will change. And sometimes you don't want to do things on the top because of a situation in the bottom in the infrastructure. And so, like I said, you need to do it all at once. That's our thesis, is that you can't just go in isolation and look at containers. You have to look at everything going on to come up with a safe and actionable answer and to get what we call realizable gains, where the change you make will actually make a difference. It isn't just a waste of time. To do that, let me talk about how Densify works for a second. It analyzes the patterns of activity to determine the settings. And I won't get into all the details of this, but basically we ingest all the raw data. We usually work with data that's already there. We have a very late forwarder that will forward us what you need out of your existing Prometheus node export your data. And we will do machine learning on that to understand the patterns of activity. This is a 24-hour pattern of what a container typically does, or what does it do on its busiest day? And what's the distribution by hour of day? How much horsepower is this thing actually using? So we look at that. I'm not going to get deep into that today in the interest of time. We have other webinars that go a little deeper on that. But we look at that for the containers, but we also look at the replication patterns. And this is very important because you could have a container replicated hundreds of times, and the replicas might have very different usage profiles, but they're all launched off the same manifest. So if you want to optimize them, you need to look at everything because you can't bring the limit down if your busiest container is busier than that. You'll clip it. So it becomes very complicated, and this is very difficult to do manually. If you're sitting at Grafana, it's hard to ingest this much data and make a decision on it. Even if you can understand the data, it's hard to figure out what the numbers should be. So we codify that in very deep policy, saying, well, when we see these patterns, here's exactly how we treat it. Here's how much history we look at. Here's the outliers we'll drop, the percentiles, and we're going to set the requests and limits based on these numbers in a very, very intelligent way. And again, there's a whole webcast just on that topic. I'm just not going to get in detail today. I just want to show the end result. The end result is we generate very precise recommendations. So for each container, you can see exactly what its current state is, what it should be, how much money that will save, how much risk that'll mitigate by making changes. And also we have this visual that I showed earlier, which I'll cover again. It's like an MRI for your container environment. You can at a glance see what's going on. Oh, it looks like I might have memory kills. It looks like I might have a lot of cost problem in this cluster or in this namespace. And so very versatile construct. It's usually the starting point to look at an environment. Once we do all the analysis and correlate all the numbers, then we can just visualize an entire company in one picture if you want and see what's going on. That's how we work in general. It's available in the UI. Of course, there's APIs. We have Terraform modules and all kinds of ways that drive automation. But the main problem is figuring out what's wrong and what it should be to address both cost and risk. So if I were to go in the UI and drill down on this and drill down, there's lots of roll-up screens, but if I get down to the per container recommendations, what we'll see here on the screen, you'll see each row is a different container and it might have a different number of replicas. And it has a whole lot of numbers here. And you don't have to read these numbers. We just roll that up as well. But we're getting the numbers here because we're looking at a container here. And again, don't look at the numbers, look at the bottom left here. It's been given 1,000 millicores. So the usage curve at the bottom is the typical usage of CPU resources in millicores. This is an interesting resource. It's pretty much concentrated just below 400 millicores all day long, but peaking up almost to 6 and going as low as, say, 150 late in the afternoon. So we see all kinds of weird and wonderful patterns here. This one's running kind of flat out, and these are quartiles. So it's peaking at the top, the minimum's at the bottom, and then the blue part is the sustained activity. So it's spending half its time in that blue thicker zone. And so we can see if things are, a certain level of sustained activity, certain level of peak activity, and we can use that through policy to figure out what these numbers should be. So in this case, the yellow line is the request, and the purple is the limit, and both are set to 1,000 millicores. And so the problem with this is this workload does not need 1,000 millicores. When you do that, the schedule will give you a CPU. And once it's given out all the CPUs on a node, it moves on to a new node. So you're actually going to strand a half a CPU here that you're never using because you asked for it, but you don't need it. And it's not like a VMware environment where you can overcommit. These aren't virtual CPUs. These are real CPUs. So that's actually going to strand quite a bit of capacity. It also never really makes sense to set the limit the same as the request for CPU, sometimes for memory, for guaranteed quality of service, but not for CPU. So we're recommending bring that request down to about half its level. You can go above your request just fine, as long as there's headroom on nodes, and it's going to save a ton of money. You can leave the limit up there, or not even set a limit in case of CPUs. But this is going to make a pretty drastic difference to the resource consumption of not the consumption and utilization, but how much infrastructure you will have to deploy to support these workloads, because you have to provide enough node capacity to meet all the requests. So when we just cut that in half, that's all reflected in these numbers, and you don't need to read all these numbers, but you can tally them up. So this environment I looked at has about 77 CPUs worth of waste in just this environment of about 1,700 containers, not even a very big environment. The memory surplus is also about 61 gigabytes. Again, this is going to impact your costs. And so you can get all that readout. In fact, if I zoom out on the far right, we can give an estimate of the costs, and we can base this on the cloud billing data to say that you're going to actually get some real savings by doing this. And that's great. But the flip side of that is that, and I'll talk about this more, there might also be risks in this environment. And so in this case, what we're seeing, these red highlights here are saying there are containers in the environment that are restarting quite a bit. And in this case, they're hitting their memory limits. So there's all kinds of reasons why we might see restarts. And I'll talk about it a bit more. But you probably don't want to go downsizing things that are already having operational problems. And I'll talk about it at the limit level and the request level as well. So it's both sides of the equation. There's usually cost savings, but there's kind of this wait, not so fast. You got to make sure the systems are working properly first before you start squeezing them and increasing container density. All that's available in a UI that, of course, you can drill down, and our latest release is coming. You'll be able to pivot on this kind of stuff and do all kinds of really cool functions in these numbers to understand the cost and risk of your environment. That's one way to look at it. Now, one of our big customers said, this is great, but can I view this for a line of business or an app team or other things? And you can view this table based on any logical grouping. I could say, just show me all my Nginx servers. But we also built a visual to do that, which is kind of a better starting point. So rather than looking at thousands of rows, this is that same data just visualized on how bad the containers are, how far wrong they are. We call this the 4-packs, and this is showing about 11,000 containers in this case. You can point this at your whole company and then see what your whole company looks like. CPU requests top left, memory requests are on the top right, and then CPU limits and memory limits. And so at a glance, we can see what's going on. It doesn't take very long to learn to read this thing. And the thing that literally stands out on this is that this big yellow bar here. So the center is things that are correct. So about just under 2,000 containers look pretty good. The red are the ones that are too small, and the yellow are the ones that are too big. And these are buckets of how too big they are. And the 500% means these ones are actually 5 times bigger than they need to be or more. The 200 is like things that are twice as big as they should be. So there's a trace of ones that are 2, 3, 4 times as big as they need to be, which is bad. But there are a whole ton that are way oversized. And we see this yellow bar in a lot of environments. FinOps is very interested in this bar because it directly translates to spend. And so I'm going to call that number 1. When we see the yellow in the top half of this diagram, it usually translates to spend. We consider that a risk. It's kind of the scary amount of spend that people see in their cloud bill, oftentimes being caused by these yellow bars in the container world. The memory, same thing, same dynamic, but it's usually a little more complex. Usually in memory, we see a mixture of red and yellow. We do in CPU as well, but it's still mostly yellow. For example, in this environment, this is a real environment, almost 1,000 containers are a fifth the size they should be for memory. So you ask for a gigabyte, but you're using 5 or 6 or 8. It can be very extreme. And this is, again, 5 times or less. So this is the bucket, the catch-all for everything that's ridiculously undersized. Gray means you don't have a value. It's unspecified, which is equally bad or probably even a bit worse for memory requests. You didn't even tell Kubernetes what you want. So I'm going to call this number 2, because if you have this situation, Kubernetes doesn't know what to do. It only bases its scheduling on requests. So if you say, I only need a gigabyte of memory, it'll say, okay, that node has a gig of unallocated memory. I'm going to put you there. And when you go and use 5, you could blow the node up. So a lot of times when we see red or gray here, it's an indication that you might have memory kills and node imbalances, where some nodes might be overstacked. And especially when we see some yellow over here, you might have nodes that are understacked. So we also have thousands of containers that are too small. You see, it's kind of a mix, and we see this everywhere. So I might have a waste of money here as well, but I also have out of memory kills at the same time. And so memory is a little more nuanced. Usually we see a savings opportunity, but the first thing to go after is these risks, because you might end up having, like I said, I'll show examples of node imbalances that are causing out of memory kills. Even in an environment that has too much capacity overall, you can have kills happening. The same is true of this one down here. And this is probably the most scary one of all, because if your limits are too low and you hit your limit, you'll get killed. The Linux kernel will kill you. It'll kill a process inside the container. It might even kill a process that's not process ID 1, and you might keep running without a process, missing something. So when we see this, thankfully, it's usually less volume than the upper ones, but they're really nasty, because you can be on a perfectly configured set of nodes, and you can be getting killed because your limit's too low. Number 3 we look for, that's probably the scariest of all 3 of these, and usually the first one you go after. 3 and 2 are both very much of interest to SREs. One is FinOps and cost, and usually you want to tackle these 2 and 3 before you unlock the cost equation. So again, it's kind of a certain order to do this. The gray in the bottom right is nasty as well. That means you didn't give it a limit, and it may or may not cause immediate problems, but if you have a memory leak, a container can consume an entire node and blow stuff up. So we've seen that happening as well. So you don't want gray. You want everything to have a limit and a request, and you don't want them to be this deep in the red, or you'll have problems. So those are 3 things that we see, the 3 scary things, one from a spend perspective, 2 from an operational risk perspective. Let me just show you some examples. So here's an example. It's kind of obfuscated, but it's a set of containers that are running. And the first 2 Tomcat servers have been given 4 CPUs each, but the surplus is 3.9. Like they are about, I don't know, 100 times too big. These aren't the curves at the bottom. These ones aren't selected, but these ones are wasting quite a few CPUs just in their own right. But this third one I want to focus on, which is the one's highlighted at the bottom. This one was given 11 CPUs, but it's got over 3 CPU surplus. which on the surface doesn't seem too bad. So if I go up to the bottom left, that's the one that's selected here. So it's running along around 7.5, 8,000 millicores. So using 7.5 or 8 CPUs. But the yellow line says each one's being given 11 CPUs. And we're saying that can be brought down, but it's replicated 128 times. So this is where the math gets interesting. So your 3 CPUs too big, replicated 128 times. That's 412 CPUs wasted by one container, by one Terraform manifest or one launch configuration, which at list is just under 200,000 a year. It's even worse than that because the third curve over, that's the busiest container of the replica set. The third curve over is the average of all the replicas, and they're 5 CPUs too big. So there's probably more like almost $300,000 of waste at list price from one container. And we see an example like this almost everywhere. That list is pretty long in the UI. You can see here, there's a ton, there's 4,000 CPUs of waste in this one. So huge opportunity to go after the waste, especially for the CPUs initially, and especially for the stuff that's in the yellow. Now, let's go on to another example of number 2. So this is where you have memory requests where some are too high and some are too low. And again, Kubernetes doesn't know what to do with that. It says, it's like throwing darts. You told me you needed a gigabyte. Now you're using 5. What's going on? Or you said you need 5 gigabyte, but you're only using 1. And so what happens is these are the nodes underpinning, this is actually an OpenShift environment, technically. So Kubernetes environment, you see the average and peak memory utilization, and they're all over the place. The peak is 18% on some nodes, 99% on other nodes. It's just all over the place. And we see this everywhere. And if I sort this, the busiest nodes in this list are all basically hitting the roof. You never see 100% in this list. Once you hit 98, 99, even 97, you're basically out of memory. There's going to be out of memory kills happening. And for example, this top one, if you drill in on a certain operational day here, after 4 p.m., it was just hitting the roof the rest of the day. And this is not good for your workloads. This causes out of memory kills. And there were tons of out of memory kills happening in this environment. But in the same node group, this is in the cluster, there's actually one node group. If I go to the bottom nodes weren't even hitting 20%. And that's what happens when all the requests are wrong. So on average, you might look okay. On average, it looks like you're 55% utilized. There's a ton of wasted memory. But because the top nodes are hitting the roof, you can't put any more containers in this environment, and they're already not working properly. And so there's savings here, but it can only be unlocked after you fix this imbalance. And you fix this imbalance by getting rid of the gray and the red in the histogram. And then these nodes will stop being overstacked. The scheduler will stop overstacking the nodes if you just give it better inputs. So that's scary situation number 2, where things are actually dying in an environment that has plenty of capacity. It's just all out of balance, and there are unhealthy nodes. And in our latest UI, you'll see node saturation, node balance metrics that you can very rapidly see. Yeah, that node group is way out of balance and has saturated nodes. Third example, I'll show memory limits. So you can be running on nodes that are huge. In fact, you can be the only one running on a node and have this happen where you see this red over here. And we've done quite a bit of R&D around this. So that's where the memory working set, not the total memory, but the working set is touching the limit. And there's a bunch of conditions here. And we also pull back, we kill the exit codes of the containers and stuff. And there's quite a bit of restart activity here. You can see that on the bottom left here. When the peak of that is tapping that purple line, that's not good. That means you're hitting your limit. You're probably getting killed again and then going back up and getting killed again. And this one got killed 1,100 times. In fact, if I look at the restart metrics, it's restarting a ton, at least up till 2 p.m. Then it seems to restart less, and then it goes up again. So this is a nasty situation. Again, you can be on a node that's completely, lots of spare resources. You can be the only one running on a node, and you can have this happen. So this is usually the first priority to fix, because this causes all kinds of weird and runnable problems. Like we've seen DNS servers bouncing, infrastructure components, queue managers, that kind of stuff. You just want to get rid of this. So it's not a cost thing at all. You can actually fix this without spending any more money. Just get that purple line up. You can see it on the bottom, on the second chart in there. Get that limit up and stop hitting it, and you'll work a lot better. It's often good to tackle those first and then go after the cost. So with that, those are examples. There's more. We have like a 12 risk poster of all the different things that can go wrong, but those are the 3 biggies: cost and operational risk. And the way this generally goes down is that if you look at the scheduler that's running containers, the little Tetris blocks of the containers, and if the dotted lines are the requests, if they're too big, you'll bloat the number of nodes that you need and waste money. And so the first step is to do the analytics I've been describing, come up with all the kinds of recommendations and the prescribed order to fix them. These numbers get modified. There's various ways to do that. I'll show an example on next slide or in 2 slides. Usually they go down for the most part, but some go up, like the limits will go up. And then when Kubernetes redeploys, just the stock scheduler, we don't need to modify the scheduler. It works great if you give it good inputs. And so if we give it request values that are more in line with the usage, it will automatically stack better. It'll use fewer nodes as a result. And we've had some discussions around bin packing. You can actually enable bin packing in Kubernetes where it'll schedule on the busier nodes first, so it uses the least nodes possible. Very difficult to use if your requests are all wrong, but it's possible to use if it looks like this because you're giving it better inputs and you'll start saving money pretty quickly. You'll just run on fewer nodes. Now, at some point, what'll happen is the node might be the wrong type of node, especially if we optimize CPU quite a bit. So what happens is the other side of our product, the cloud side, will go and analyze all the nodes and the scale group replication patterns in our scale group analysis and say, okay, you should no longer be on an M, you should be on an R or some other type or a C, whatever that is. You've got more CPU than you need on the floor. Let's tighten that up, which saves even more money. So usually there's kind of this elastic phase where you just run on fewer nodes. Then at some point, you'll get a recommendation saying you can use a different node now and save even more money. And of course, we're also constantly making sure you're on the latest nodes. There are actually 8 out now. We're just working with a customer on that to make sure that you're constantly on the latest, fastest, best gear. That's why we call it full stack because it's all working in unison. The left side will automatically give different answers as you tackle the right-hand side. It often even gives a better answer right from the start. It just says, look, even with your current request, you could be running on a different instance type and save money or have less risk. So it all works seamlessly together. And the node group side, I'll just show this quickly. This is the other side of the product. These are all scale groups where we see all the patterns of utilization, all the IO. These automatically link up to the Kubernetes clusters and we'll get all the request values in here as well. And the replication patterns. And we'll say, you know what? You have a min and max set to 4 right now. It's 4 and 4. You see up here, we're saying you could bring the min down, push the max up. You'll get more elasticity. You'll save a ton of money. This thing will flex throughout the day. And then as you optimize the containers, this analysis will change and say, okay, now you can go down to one node at your least busy time of day, or now you can run on a different node. It all works together and happens automatically, and it can all be automated. On the automation theme, and last slide, and then I'll hand over to Chuck again. Here's just an example of how that works. Is one of our customers that was pretty early on automating. I'll just build this out. Every time they deploy a container, this is an OpenShift environment. This happens to be running on-prem. Every time they deploy a container, they hit our API and get the best, latest numbers and just inject them in the template every time they go out. So that's one way to do it. It's pretty slick. They do this for everything. We have a Terraform module as well. So you can just put a line of code in your Terraform if you're using Terraform, and it'll automatically happen as well. And in doing so, this is what their environment looks like. And this is what good looks like. Huge green bar, meaning the vast majority of the containers are all correctly sized. There's no gray, so good hygiene. Everything has a value. There's a bit of red and yellow, and that's a byproduct of the fact that the policies don't make too big a change at once. So we're not going to go take away 99% of your CPUs in one step. So usually it converges on the green. As new things pop up, they might be in the yellow, and then they get fixed. But this is what good looks like. And they saved half their new infrastructure spend doing this. And I recently did a podcast with them. There's some information on them on our website. So this is what good looks like. I mentioned we have Terraform module. There's various ways to automate. And when you do that, then it all just works better and you save money. So with that, I only left 1 minute for Chuck. Sorry, Chuck, I went a bit long, but I'll let you close it up.
Thanks, Andrew. It's such a powerful platform, but so many interdependencies, as explained by you, so many things to think about as you provide resources to these environments. Just a couple of quick questions from the group. Support for managed Kubernetes from the CSPs, EKS, et cetera.
Yeah, absolutely. We support all of those. They're very common. The container side of the analysis I showed with the histogram is the same for any deployment of Kubernetes, on-prem, bare metal, whatever that is. The node side changes a bit, but yeah, EKS, AKS, we link them up to the scale groups that are underpinning them automatically. So that works. If you're running Carpenter, then again, it's a slightly different approach of not scale groups, but all the same analysis works and you get the same benefits from it. So yeah, pretty much any flavor. There's just differences on the node side, how, or even if you can change the nodes. And if it's on-prem, for example, then it becomes more of a capacity management challenge of, should I buy more nodes or when do I need to buy more nodes? It kind of varies on the node side, but the container side is identical.
A comment and question, if Kubernetes is restarting things or the containers restart, does it matter that things are falling over?
So great question, because it really comes down to frequency. So most apps are designed to survive a restart of a container. And there's lots of different reasons they can restart. So they might not restart because of a memory problem. They might fail to open their port, fail to initialize, all kinds of stuff. And most apps are architected to survive that, but not in the volume I showed. So whenever we work with a customer, when we see the volume up there that you're getting 10 restarts every 5 minutes, then things start to go horribly wrong because queue managers back up. It's just disruptive. Again, we've seen DNS servers doing that where yes, they restart, but it was disruptive. And still, yes, maybe you can survive that in certain architectures, but it's best to make it stop if it's just a matter of fixing the limit. Great question. Yes, a few of them aren't that problem. Most apps survive. A lot of them are a problem. The hidden kills I kind of alluded to, where if you have hit your memory limit and process ID 1 is not the one killed, if process ID 1 gets killed, the whole thing restarts and you can see it happen. If it kills any other fork process, the thing keeps running. And there are newer updates where this can stop happening, but it's not out in the wild yet. But you can actually just lose your data loader and you get what's called zombie pod, and nothing can really survive that. So we see cases where hitting your limit can actually cause process kills that don't cause a restart. And again, it's very hard to architect an app to survive any random process getting killed. Again, there's lots of examples that we see in pretty much every one of our customers.
I will call your attention to the very rapid and simple trial process we offer. Welcome you to explore that with us if you have an environment of some scale, or if you're planning to have an environment of the scale that we talk about here. Densify and this functionality is really targeted at larger enterprises. So we do call that out as a minimum. We invite you to visit the trial page on our website, and you can just ask us questions about it if you'd like to explore that. We will be at KubeCon in Salt Lake City in the middle of November. We are also at FinOps X in Europe, in Barcelona. Same week, actually, the week of November 11th. So if you're attending either of these events, please look us up. Love to talk to you, show you a live demo.